today we are going to be looking at predator-prey models. So I am going to let S of t equal the number of prey at time t, and then we're going to let W of t equal the number of predators at time t. Your book used different letters for their predators and preys, but it was like R's and something else, and that was not helpful to me. So S for sheep, and then W for wolves to help me keep it straight. So, do you have any idea of like any relationships between these? Any ideas?
When the sheep differential equations look like their reproductive rate minus the rate at which the wolves kill them, and they're like that, right?
Yeah, exactly. So the sheep's differential equation should look like their reproductive rate minus the rate that the wolves kill them. So let's break that down a little bit. So if there were no predators, then the prey is proportional to its population. So that would be the differential equation ds dt equals a times s for some s greater than 0. Right? That's any population when you're not worried about like outside forces that grow exponentially, right? It's just its growth is proportional to its population. So that the growth is proportional to its population, where A is that like proportional factor that we're dealing with. Okay? What would happen if to the predators if there were no prey? They would die, right? So if there's no prey, the predator decays proportional to its population. So we're going to represent this as dw dt equals, and then I'm going to go with negative bw so that we can keep all our parameters greater than 0. But that thing in front of the w needs to be negative as a whole because the population is decaying, right? Okay? And then the last kind of defining factor that Pat mentioned is for your sheep, for your prey, its interaction with the wolves is going to decrease its population, right? So we have that the number of encounters between the predator and prey populations right? We need to know how often they're interacting. If they're in different silos, it's not going to matter, right? So to represent this number of interactions between the predator and the prey populations, we're going to represent that as a product S times W. So that's how many times they're going to interact with one another. Now, there are factors that are going to affect how those interactions go, and we're going to represent those with parameters. So let's write our entire ds dt. So ds dt is going to start with A times S. So that's the growth of that sheep population if it was uninhibited. And now, do you think we're going, and now we want to do something with this population or this interaction S times W. What do you think I need in front of this? Minus? And then what else? Some other factor. We'll call that factor C. Okay? So that C factor is going to determine how often that results in a decrease in the sheep population, right? Because potentially every time the sheep encounter wolves, like 10 of them die. Or maybe every time they encounter, one of them dies. Or maybe not every time they encounter, there's not a certain number that die, maybe like every other time. So that's that factor C that's accounting for that. Okay. Anybody think they have dWdt? You know the start of it. Negative BW. Okay. Yeah. Y plus DSW.
Measuring interactions between sheep and wolves. It's not necessarily going to be C.
Yeah. It's not going to be C. And interactions between sheep and wolves is good for wolves. It's bad for sheep, right? So we have to grow the wolf population somehow. So it's those interactions that is going to grow them, because if they're interacting and getting food, they are not dying off. Okay? And so for all of these, we're going to have A, B, C, and D be greater than or equal to 0. These are called the Lucca-Volterra equations. All right, so we have these equations. Are these linear or nonlinear differential equations? Nonlinear. What makes them nonlinear, Evan?
Populations interact.
Yeah, the populations interact. So we have this times SW, right? So we have variables multiplying one another, so it makes it nonlinear. Perfect. So if you wanted to find the critical values, the equilibrium values, how would you do that for this one? Okay, that's a great start. So another way of thinking about the question I asked is, how are we going to be analyzing this? Okay, so Nico wants us to find equilibriums. By setting equal to 0 and solving. So that would give us our equilibrium values. But with non-linear equations, we like to do a little bit more to talk about those equilibrium values, right? We like to try and classify them as stable or unstable or centers. So how can we do that?
Find eigenvalues and classify from there.
Right. So if it was linear, we could find the eigenvalues and classify from there. But we need to take another step. So last week with Dr. Thomas, you guys talked about finding the Jacobian and looking at the eigenvalues of the Jacobian, right? So that's what you are going to do. So that I can refer to it, let's call this function f a function of s and t. Not s and t, s and w, I'm sorry. And let's call this g a function of s and w. Okay. So we are going to linearize using the Jacobian. So we're going to take j. Anybody remember how to find the Jacobian? Perfect. Each partial derivative in a row. So we're going to have f with respect to x, f with respect to w, g with respect to s, g with respect to w. And then, after you find the Jacobian, you can substitute in your critical values or your equilibrium points, and then analyze those eigenvalues. So then you can classify using eigenvalues. So you guys did this last week with the Lorentz equations, is how you started discussing them, which was a three-dimensional Jacobian matrix because you had three differential equations. This was a little bit easier because it's two-dimensional, but still interesting. Okay. Any questions about that? All right, let's do number one on your in-class assignment. You've got lions and gazelles, you're finding the equilibrium values and classifying. And then also let's sketch the phase portrait.